Welcome to this course on control engineering. In this first module, we will establish the fundamental principles of how engineers model, analyze, and design systems that regulate behavior and performance. Control systems are everywhere around us, from household appliances like washing machines and refrigerators, to industrial machines, aircraft, cars, and even power generation plants. The central idea of control engineering is to make systems behave in a desired manner. To do that, we need mathematical tools, models, and analytical methods. In this module, we will cover linear approximations of physical systems, the Laplace transform, transfer functions, poles and zeros, time constants, signal flow charts, state variable modeling, feedback, and transient response. 1.1 Linear approximation of physical systems. Physical systems, whether mechanical, electrical, or thermal, are usually described by nonlinear equations. However, nonlinear systems are often very complex to analyze. A common engineering practice is to approximate these systems as linear systems within certain ranges of operation. For example, the motion of a pendulum is nonlinear because of the sine function in its governing equation. But when the pendulum swings only through small angles, the sine function can be approximated as linear. This makes analysis much easier. Linear approximations allow engineers to use powerful mathematical tools such as the Laplace transform to model and analyze system dynamics. 1.2 The Laplace transform and the S-plane. The Laplace transform is a mathematical technique used to move from the time domain, where equations are expressed as differential equations, into the frequency domain, known as the S-plane. In the S-plane, differential equations turn into algebraic equations, which are easier to handle. System behavior, stability, and response can be studied by examining the location of poles and zeros in this domain. This is one of the most important tools in control engineering because it connects system dynamics with visualization and analysis. 1.3 Transfer function as a concept. A transfer function describes how input signals are transformed into output signals in a system. It is expressed as a ratio of output to input, assuming zero initial conditions. The transfer function captures the essential dynamic behavior of a system. It helps us understand how the system responds to different inputs, and it is used in designing controllers to achieve desired performance. 1.4 Poles, zeros, and the time constant. The poles of a transfer function are the values in the S-plane where the system output becomes unbounded. They indicate the natural behavior of the system. The zeros are the values where the output becomes zero, representing frequencies that are blocked or diminished. A time constant is a measure of how quickly a system responds to changes. For example, in a simple heating system, the time constant represents how long it takes for the system to reach about 2/3 of the final temperature after being switched on. Poles, zeros, and time constants together give deep insights into system performance. 1.5 Signal flow charts. Signal flow charts are diagrams that represent the flow of signals through a system. Each node in the diagram represents a variable, and each branch represents a functional relationship. Engineers use signal flow charts to visualize how inputs are processed into outputs, how feedback is applied, and how different components interact. They are particularly useful in large, interconnected systems. 1.6 Modeling linear time-invariant systems with state variables. Another way to model systems is through state space representation. Instead of only focusing on inputs and outputs, state space models describe the internal state of a system using variables. These models are powerful because they can represent multiple input and multiple output systems, and they work well with modern digital control systems. 1.7 Feedback and second-order systems. Feedback is one of the most important principles in control engineering. By feeding a portion of the output back into the input, systems can correct errors and maintain desired performance. A classic example is the thermostat in your home. It measures the temperature and adjusts heating or cooling to maintain comfort. Second-order transfer functions are especially important because many systems behave like second-order systems. The poles of these functions determine how the system responds, whether it oscillates, overshoots, or smoothly reaches equilibrium. 1.8 Transient response and error analysis. Transient response refers to how a system reacts when subjected to a sudden change, such as switching on a motor. Engineers study transient behavior to understand overshoot, settling time, and oscillations. Errors in feedback systems are also critical. A control system may not perfectly reach the desired set point. The error in equilibrium, also called steady-state error, is an important measure of accuracy. Engineers design controllers to minimize these errors. 1.9 Feedback stability in the time domain. Stability means that the system responds predictably without running away or oscillating uncontrollably. Feedback can improve stability, but it can also destabilize a system if not designed properly. The relationship between the location of poles in the S-plane and stability is straightforward. If all poles are on the left half of the S-plane, the system is stable. If any pole lies in the right half, the system becomes unstable. In this first module, we learned how to approximate physical systems as linear models, use Laplace transforms and transfer functions, interpret poles and zeros, and analyze time constants. We studied feedback, second-order systems, transient response, and the relation between poles and stability. These concepts form the mathematical and conceptual foundation of control engineering. In Module 2, we will apply these ideas to frequency response analysis, controllers like PID, laboratory measurements, and safety considerations.